Buonasera.
Buonasera a tutti, benvenuti
Avete visto che
a questa
non è un
diretta,
pesce.
che non è un pesce, non è uno scherzo. Abbiamo davvero Jocelyn Bell Burnell in diretta con noi, scopritrice delle Pulsar, quindi questa sera sarà una diretta speciale, sarà un onore avere con noi Jocelyn. Facciamo questa piccola introduzione in italiano, ma il resto dell'intervento sarà in inglese, quindi potrete seguirlo in inglese e poi lo trovate sottotitolato su YouTube prossimamente. So, thanks again, Jocelyn, for accepting our invitation. So we are so proud to have this live streaming with you. And you can start your presentation whenever you want. And at the end, we can
make some questions.
Yes, from the public.
Thank you. And thank you for
Thank you again.
putting up this PowerPoint. Did you know in Switzerland there is a political party dedicated to the removal of PowerPoint? A very important political party.
Really?
Yeah. Apparently.
It is a very good idea.
According to Wikipedia.
I understand them. I would vote for them.
So the invisible astronomy is mostly radio astronomy, astronomy at radio wavelengths. The invisible people, well, maybe that's the women. We'll see. Thank you. Could we do the next slide? So I'm going to tell you a story from radio astronomy about the discovery of pulsars. And if time permits, I will also describe how pulsars were nearly discovered several times before the real discovery. A little bit about the factors that I think led to the discovery, and if there's time, a little bit about what happened next. Can we do the next slide? So I am not Southern English. I come from the north and west of Britain. And when I come to Cambridge, it is full of young men. There are very, very few women. And the young men are certain that they are very clever, God's gift to academia, and that they have an absolute right to be in Cambridge. And I am an outsider because of geography and because of gender. And I quickly suspect they have made a mistake giving me a place in Cambridge. Within the first week, I get given these tools. These are my tools. I still have them. They are not microelectronics tools. They are full-size wire working tools. And I used them a lot in my PhD. The next slide, please. Because I spent 2 years helping build a radio telescope, a telescope that picks up radio waves from stars and galaxies. For people interested in the technical details, they are given below the picture. The picture is of my technician, Don, on the left, and myself on the right, working in the field where the telescope was being built. I have been putting plugs and sockets on some special cable, and we are checking that the connections are good. It's quite hard working in the field like that, but I did a lot of it for those first 2 years. The radio telescope was huge. 57 tennis courts, over 1,000 wooden posts, over 2,000 antennae, 192 kilometers of wire and cable, and it worked at the radio frequency of 81.5 megahertz, which is quite a low frequency or a long wavelength. And the next slide, please. This is the finished article. You can see lots of wooden posts. Their job is to keep everything up above the wet grass, because wet grass is an electrical short. So you keep your antennae and everything up high. The telescope operated as an interferometer. We could steer it in one direction only, and we typically operated with 4 beams at a time. When I came to Cambridge, I was surprised to find they were still using valves or vacuum tubes for the receivers. I had used transistors as an undergraduate, but no, Cambridge was not using transistors. They're noisy, they're unreliable. We use vacuum tubes, or we use valves. They did ultimately change to transistors, but not then. Thank you. Next slide. The purpose of the project was to find more quasars. At that time, quasars had been recently discovered, and there were only about 20 quasars known. Quasar is short for quasi-stellar radio source. Very strong sources of radio waves, but extremely compact, not extended like a galaxy, but compact like a star, hence quasi-stellar. And because they were compact objects, when the radio signal from a quasar came to the Earth, it came through the space between the sun and the planets, and that space is not smooth. There are clouds of higher density, and they bend the radio waves. They also move, and so if you're observing a compact source, small angular diameter source, its intensity goes up and down, like you see in the bottom of the picture. Only quasars do that. Radio galaxies were much broader, much more extended, and gave a much steadier signal. So we look for signals that jump up and down, signals which scintillate. And you can see the timescale is quite fast as well. Thank you. And the next slide. So the idea was to map the sky over and over and over again, to look for the radio sources that changed their brightness, that scintillated, and maybe be able to measure their angular diameters as well. It took us 2 years to build the telescope, and then I spent half of my final year observing with that telescope. And I found lots of quasars. We started with 20 quasars. By the time I had finished, we had almost 200. So a good number of quasars. Thank you. And the next slide, please. At that time, the University of Cambridge had one computer only. It was made with vacuum tubes, not transistors. It took up a whole room, a complete room, and it had memory like your laptop. So very few people could use it. And we did not have the possibility of using that computer. The data came out on rolls and rolls of paper, like you see in the picture. 30 meters of it a day, 120 meters for a complete sky scan, which took 4 days. And in 6 months, I had over 5 kilometers of that paper. And I have checked every centimeter of those 5 kilometers. Next slide, please. I picked up lots of twinkling quasars, which was good. I also picked up radio interference. It's a very big antenna. It's very sensitive. In those days, cars were not properly suppressed. So when a car drove down the nearby road, I would pick up signals from that car. But that's the interference. I got used to recognizing quasars. I got used to recognizing interference. A few occasions there was another signal that I didn't understand. And it's labeled here as CP1919. It looks different from interference. It also looks different from quasars. And the first few times I saw it, I logged it with a question mark. But after 3 or 4 times seeing it, my brain said, "You've seen something like this signal before that you decided was not interference and not a quasar. You've seen it before from the same part of the sky, have you not?" And then it's easy. We're surveying the sky in strips, declination strips, and I store the rolls of chart paper in shoe boxes labeled with the strip. So this is the 20-degree strip. So I get the shoe box for the 20-degree strip. I take out all the rolls of chart paper and I spread them over the floor. The graduate students worked in an attic in the roof, and there was a lot of floor space. So I line up all the charts so that they have the same right ascension in a line. And yeah, there's the one I've just seen. It wasn't there last time, nor the time before, but it might have been there the time before. I didn't notice that. No. Yes, I logged that one. And yes, I logged that one. And yes, I logged that one. And they're all at the same right ascension, the same part of the sky. But what is it? I showed this chart to my supervisor. This was actually the first sighting, the slide shows. And he rightly said, "Look, the signal occupies 5 millimeters. We cannot see what's going on. We need an enlargement." And with chart paper technology, an enlargement is easy. You run the paper faster under the pen. The paper goes faster and it all gets spread out. Except if I left the chart running at that speed, it would get through the whole roll of paper in 20 minutes. And I would have to live at the observatory, putting a fresh roll of paper in every 20 minutes, day and night. Not so clever. Next best idea. The graduate student, Jocelyn, goes out to the observatory shortly before this bit of sky is visible. Switches to the high speed, lets it run for a few minutes past, and then switches back to normal. And I did that for about a month, and the source had disappeared. And my thesis advisor was furious. It was my fault. I'd missed it. And then one day I got it. And it was a string of pulses. With the next slide, please. So the labeling came later. Along the bottom, there are 1 second time marks. The top trace is the signal that came in. And you can see that there are pulses. They're equally spaced, although some are missing, but even so, it keeps the beat. It goes bump, 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 and so on. And the period is a little bit over 1 second, 1 1/3 seconds. This is a puzzle. Stars are big things. Big things do things slowly. This is fast. It can't be a star. But it's keeping its place amongst the stars. quite accurately. I was told to keep observing it. We can see that the pulses go up quite fast. That means it's small. We can also see it's keeping the same pulse period, and from day to day, it keeps the same pulse period. It's not getting tired, so it's big. So it's big and it's small. Aha. I was responsible for the nickname Little Green Men, which you can see written there. It was a nickname. I did not seriously believe it was Little Green Men, but it certainly was a puzzle. And for a long time, we only had one. And then I found a second one, and that's much better. If there's more than one, this might be some new kind of star. And shortly after that, I found a third and a fourth. So we now have 4. This must be something out in space. But Tony, my supervisor, was still a bit worried about it being Little Green Men. He reckoned that if it was Little Green Men, they lived on a planet which went round their sun. And as their planet goes round their sun, when it's coming towards us, the pulses pile up on each other. And when it's moving away from us, the pulses spread out. Small boys know about this. If I'm a small boy playing on the floor and I go, meow, you know that I'm playing with a car. And as the car goes past me, its note changes. It goes, meow. Similarly for the Little Green Men, if they are orbiting a planet, a star, sometimes they're coming towards us and the pulses get piled up on each other. And sometimes they're moving away from us and the pulses get spread out. So you go from meow to meow. And we looked for this. And we found some evidence for it. But you can get the same effect if you are moving and the car or the Little Green Men are stationary. It's called Doppler Shift, and Doppler Shift happens if the observer moves and or if the source moves. And we are on a planet, Earth, that is moving around the sun. So we had proved that the Earth went round the sun, but otherwise not making much progress. Until I found some more. The next slide, please. I think I've probably said most of this. Thank you. A colleague managed to get back a slide. Thank you. A colleague managed to get an estimate of the distance of the source doing a dispersion measurement and showed it was about 200 light years away, which puts it well beyond the sun and the planets, but not so far away in our galaxy, nearby in the Milky Way. I've talked about the Doppler effect already. The next important thing was I found a second, and then a third, and a fourth. So it's not Little Green Men. There are not 4 lots of Little Green Men, all signaling to planet Earth. Why? It has to be something natural. We published a paper announcing the first one, and shortly afterwards, another paper announcing the next 3. And there was a huge amount of publicity and interesting what the press wanted. Typically, my supervisor, Tony, and I would be interviewed together. And they would say to Tony, what is the astrophysical significance of this discovery? And Tony would tell them. And then they turned to me for what they called the human interest. How tall was I? Would I describe my hair as brunette or blonde? No other colours were allowed. What were my body measurements, my bust, my waist, my hip? How tall was I? How many boyfriends did I have? And the photographer wanted me to undo some buttons on my blouse. The treatment of a young woman was as a sex object, not a scientist. Whereas my supervisor, male, senior, he's a scientist. One good thing came out of the press interviews. We were interviewed by Anthony Michaelis from one of the UK's reputable broadsheet papers. And he said, what are we going to call these things? And we had thought about that. We wondered whether we should call them pulsating radio sources or pulsed radio sources, and decided on pulsating sources because pulsed suggests there might be somebody or something making the pulses, little green men, and we didn't want that. So what were we going to call them? Pulsating radio stars. No. We need a short name. And he suggested Pulsar. So that's where the name comes from. Next slide, please. So going on from that, I wanted to tell you some of the stories about how pulsars were nearly discovered. Because one of the nice things about having found pulsars is every so often somebody comes to me and says, you know, I nearly discovered pulsars, and tells me the story. So here are some of these stories where pulses were seen but not recognized. And the first one is summer 1957, way before pulsars were discovered. We're in Texas at McDonald Observatory, and the telescope is open to the public. The telescope is set on the Crab Nebula and a curious star in the center of the Crab Nebula, which we now know is a pulsar, but we didn't at that point. Members of the public step up to the telescope, look through the telescope and say, oh, magnificent, fantastic, oh, or whatever visitors say. A young woman steps up to the telescope and says, that star's flashing. The night assistant starts to explain how stars twinkle, scintillate. She stops him. No. I am an airline pilot. My job is to fly aircraft, new aircraft, from the manufacturer to the customer. I fly at night. There's not much to do except look at the stars. I know about scintillation, that star's flashing. We now know that that star is a pulsar, and it's a fairly fast one, about 60 hertz. We also know that some people can see 60 hertz. In Canada, the main power supply used to be at 60 hertz. Some people could see that. Particularly young women, it turns out. So we think that young woman actually saw the Crab pulsar flashing at optical wavelengths, but nobody followed up. The young man who was there tells that story to all his students. Always follow up anomalies. Always follow up anomalies. The next near miss involves the same pulsar. In 2007, Australian radio astronomers have been studying pulsars for some time. There's a catalogue of pulsars online, and this email comes in from a man now in his 80s saying that he used to work for the United States Air Force. He was posted to Alaska to look out for missiles coming in from Russia. When it was quiet, he was allowed to play around with the equipment, and he used the receivers and discovered what he says, 14 pulsing signals, 14 pulsing stars. He makes a note. To the next slide, please. He makes a note of the right ascension and declination. He did an astronomy course at college, so he knows about coordinates on the sky. And illegally, he takes with him at the end of his service that bit of paper with the coordinates of these 14 pulsing sources. He's just found the online catalogue, and several of his pulsing sources are in the Australian catalogue of pulsars, including the crab one. He probably had observed the crab pulsar. And the next slide, please. I think I've probably said all of this. He was 81 by the time he discovered this and very excited. And the next slide, please. The next story again involves the same pulsar. It involves a woman called Sue Simpkin. She grew up in Canada. She grew up in Canada at the time when its mains frequency, its power supply, was at 30 hertz. And she said it drove her crazy because she could see everything fluctuating. She could see 30 hertz fluctuations. She's going to be taking an image of the Crab Nebula, and a Dutchman, Lo Vulture, asks her to take a spectrum of that funny star in the middle of the Crab Nebula. She does. She says the spectrum's dull, but she could see some kind of flickering, or as if there were waves going out from it. Remember, she's at this stage a young woman, and she knows from her Canadian experience that she can see these frequencies. When she told Lo Vulture, he said, no, couldn't be. But when the pulsar was discovered, he accepted that she must have seen the pulsar or the effects of the pulsar. And the next slide, please. I'm not going to name the observer here because he was, although he's now dead, he was always very embarrassed about this. A group of radio astronomers were mapping the sky, the whole of the radio sky, at a frequency of 408 megahertz, using the biggest telescopes they could get time on. They'd been at it for a long time. They are now, they think, in the last week of observing, just filling in 1 or 2 gaps in their map. They use pen recorders. We don't have better technology at that time. And one of the pen recorders misbehaves. It sticks every so often. Well, the way you solve a sticking pen recorder is to thump it. And that usually gets it going again. So in the early hours of one morning, that pen recorder started going wheep, 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 wheep. And the observer says, damn it, and thumps it. And it went back to behaving normally. We now know that he had been accidentally observing a pulsar. Go to the next slide, please. It's the pulsar 0329 plus 54, which is much loved by Northern Hemisphere astronomers. But when the pen stopped misbehaving, as he thought, he said, good. He put on his coat and he went home to bed and did not write anything in the logbook. If he had written something in the logbook about the behavior of the pen, they could have claimed prior discovery of that pulsar. Always use your logbook, students. And perhaps what was less clever was following the discovery of the first pulsars, the team did not go back through their data and see if they had picked up any pulsars. I guess because the team had disbanded. They'd all gone to different places by then. But that was a near miss. An Italian, a very able Italian astrophysicist, the late Franco Pacini, a few months before the discovery of pulsars, had a very important paper published in Nature, which is the magazine, the scientific magazine to publish in. We knew that the Crab Nebula was the remains of a star that had exploded in 1054 AD. The Chinese observed it. That's well established. The puzzle was why the Crab Nebula was still shining brightly. It's some of the debris from that explosion, and whilst it would shine brightly soon after the explosion, several hundred years later, it should have dimmed, and it had not. And this was one of the big puzzles at the time. And Franco proposed that in the middle of the Crab Nebula, there was a neutron star, the remains of the supernova, the explosion, that this neutron star had a large magnetic field and its axis was inclined to the spin axis. And so as it rotated, it produced a kind of radiation, a kind of energy that could not escape from the nebula, was dumped in the nebula and kept it shining. And in advance of the discovery of pulsars, he was absolutely right. He was a fantastic scientist, was Franco Pacini. Thank you. Factors that led to the discovery. Give me the next slide, please. I had my own telescope and receivers, and I made it my job to understand their behavior. I knew what was normal. I knew what was abnormal. I was a research student, a graduate student, so I had time to follow up anomalies. And I was being very conscientious because I was certain they were going to throw me out of Cambridge, and I was working my very hardest so that when they threw me out, I would not have a guilty conscience. This was one of the first observations with short time constant. And we weren't aware of other observers doing similar work, so we could focus on really understanding what was going on. We weren't in a panic. Next slide, please. We, in Cambridge, had a good address. If you are going to find something very unexpected, even outrageous, having a good address is a great help. They know you're not stupid. In Britain, there was a fashion for when you got money for a project to say what the objectives of the project were, what the targets were, and then your success was measured against how many of those targets you had met. Perhaps more importantly, if we had had computers, would we have programmed the computer to look for something we didn't know existed? And it's changing now, but low frequencies for a long time, low radio frequencies have been neglected, and the time domain has been neglected by many people. It's beginning to change now. There have always been people interested in pulsars, and now we also have things like fast radio bursts and transients of all sorts. So this is changing. And the next slide, please. So as I finished my PhD, I got married. I got married to a man who worked in local government. The way you progress in local government is to move to another locality. And so we kept moving. There was a child, but mothers were not expected to work. It was proven that if mothers worked, the children would be delinquent. So no facilities for childminding, or very few. Next slide, please. So my subsequent career has really been a string of jobs. Some of them quite lowly, but all of them fun. I don't know if in Italy you have a game called Snakes and Ladders, a ball game. My career felt a bit like Snakes and Ladders. Climb a ladder. Then husband says it's time to move, slide down a snake, find another ladder, climb up that. Husband says it's time to move, slide down a snake, etc. Next slide, please. So this is the whole spectrum. I've worked in radioastronomy at the left-hand side, millimeter, left of center, infrared, just about center on this diagram, X-ray off to the right, and gamma rays on the far right. And often arriving in one of these fields just as it boomed, became huge fun. So it's been a great career, but it's been not typical. Next slide. So I've been a researcher, a lecturer, a tutor, a manager, a professor, a head of department, a dean. I've done public relations and outreach. The next slide, please. I think I'll skip that one. Thank you. And the next one. And the next one. So I've had a lot of fun doing all sorts of different things, but because I was female and because I was a mother, it's not been an orthodox career. It's been very anomalous, different. It has, however, been huge fun, and it's been great talking to you this evening. So thank you for your interest. Thank you for your attention. Thank you.
Thank you, Dr. Bell, because this is really an incredible chance for our science communication project and for our followers to hear the history of pulsars and radio astronomy from, I guess, one of the main characters of this story. They are also complementing with your English because it's perfectly clear and understandable. We're talking very, very paced. And we had a comment from a person that says, good evening, Dr. Bell. I'm happy to tell you that my son, whom you were so kind to meet via Zoom last May for his middle school short research on pulsars, is now among the 30 national finalists for the Astronomy Games in Italy. Thank you so much for being such an inspiring person.
That's brilliant. Well done.
This is Alexandro Lai.
Thank you.
So I guess we can now take questions from our viewers, and I don't know if Matteo and Filippo have already some of them ready for reading.
Yes, I have a couple of questions from my side. So just to well, a lot of questions really, but well. So I think a couple of them. Something related to the dispersion measurement of the signal. So how do you know whether you were detecting the same pulse or whether you are detecting the next pulse over in your measurement? So this is something related to your discovery. Yes.
Yes, the way we did it was to take two of my receivers, tune one up a little bit in frequency and one down a bit in frequency. And so it would go blip, 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 blip.
Okay, yeah.
It was the same pulse. We just had to measure the time difference between the blip and the blip and know how different in frequency they were.
Okay, clear, thanks.
I have a question as well. How seriously your supervisor Tony was concerned with the little green man hypothesis before the discovery that the signal did not show a Doppler change? Because you said that you didn't believe that at all, but was he, and how much?
We were really very puzzled about what the signal was. I remember doing a calculation to see if it could be a satellite in some curious orbit. I couldn't find a satellite with an orbit of 23 hours, 56 minutes. So that one went away. It was one of the checks you would do anyway. Observe it at two adjacent frequencies. No, sorry, I'm answering the wrong bit of question. LGM, Little Green Men, was actually my nickname for it. And maybe that was leading my supervisor a bit. But also, I think he was genuinely concerned, at least when there was just one, that it might be Little Green Men, because I was told to keep very quiet. Once you get 2, 3, and 4, no way. There aren't so many Little Green Men. Does that answer your question, Filippo?
Perfectly, thank you.
We have a question from Paola Pavesi, which is regarding your unorthodox career and the fact that maybe things have changed. So she's asking, how do you judge the modern situation of women scientists? Has something changed respect to your experience to 30, 20 years ago, or do we still have a lot of work to do?
I can only talk about the situation in Britain. I don't know enough about other countries. The situation in Britain has changed dramatically recently because of something else I was involved in. I and some other senior women were concerned about how few women there were in science in Britain. And we thought it was to do with the culture in the universities. It's not women's brains, they're okay. It's the ambiance in the department. And we wondered how to help this. And one of us said, vice chancellors, that's rectors in your language, is that right? The head of the university? Yes. Rectors are competitive men. They were all men at that stage. If we create a competition, a prize for the most woman-friendly university, they will compete. Well, we were poor, but we got a glass rose bowl. We announced the competition, and several universities competed, and we awarded the glass rose bowl. Next year, more universities compete, and we award a glass rose bowl. And that went on for a few years. And then the funding body, the Research Council, thought, this is a tactic, and started asking universities to provide information on how many women they had, how many professors, how many students, how many at each level. And then made it a requirement of getting funding that they were recognized by our group as women friendly. In other words, that they could get the glass rose bowl. And when funders start applying pressure like that, your department must demonstrate that it is women friendly, or you will not get any research money, then suddenly everybody takes notice.
Of course.
Well, that happened in Britain. Then it was extended to arts and humanities, where there are lots of women, but no men. And then it went to other parts of Europe. It grew quite dramatically. It went to Ireland. It's coming in the United States, where it's also linked with race and sexual identity, gender identity. And when a funding body applies that kind of pressure to a university, you know, things change quite fast. It's shocking, but it's true.
Makes me think also about climate change, that as long as everybody's just talking about it, oh yeah, we have to do something, we will. When you start putting financial pressure on this kind of stuff, immediately balls start rolling and everything changes in the blink of an eye.
Yeah.
There are a lot of thanks towards our guest, so Dr. Jocelyn Burnell, for her perfectly clear talk and her explanations and her kind answers to our questions. I don't know. Filippo, Matteo, do you have other
Yes,
questions?
there is a
Do I
question
take another one?
from
Go on, Matteo.
Gabriele Bertinelli. So we're back to science. So we know that pulsars emit electromagnetic beams and that we receive them as pulses with the pretty regular periods. So these pulses, if you look in more detail, consist of a dense family of micropulses. What is the cause of these micropulses, in your opinion, or if we have something from
There is a bigger question. What is the cause? We still don't really, well, one or two people think they know how we get the pulses. Obviously, the rotation is part of it, but how do you get this beam, which then rotates? It's a very difficult topic. The electric fields are huge. The magnetic fields are enormous. The charge density is high. It's very difficult physics. It's relativistic. It's a real mess. But there are a few people who believe they can explain how the radio beam is produced. That then, since we still don't have real great understanding of how the main radio beam is produced, how details of the radio beam are produced are beyond me. It's too difficult.
Okay, other questions? Philippe, do you have something for our guest? Or do I take another one? You're muted.
You're muted, Filippo. Okay. Now you are not muted.
Okay. Someone is muting me for no reason.
Because not to superpose with the voice of Jocelyn, because she has no noise cancelling or earplugs, so there is a bit of an echo. So anytime she talks, I mute everybody else.
Okay, so I'm searching for
the last one, from Giuseppe Lidrieri.
I show it. Okay. No, the wrong one. Okay.
It's this one.
Right.
It's an honor to listen to you, Dr. Bell. Is every neutron star also a pulsar? We consider a pulsar only when the radio ray is sent to Earth.
Mm-hmm.
Yes. Second one.
There probably are also, I'm sure there are also pulsars that we do not see because the beam does not sweep across the Earth. It goes somewhere like that, and we never see it. So that's undoubtedly true. And we also know that pulsars gradually evolve, age, probably die, although I don't think we have seen one die yet, but they will sooner or later die. So then we will stop seeing them. But the main factor is we only see the ones whose beam goes across our faces.
And regarding, I saw maybe a question earlier, I don't remember anymore the author. Regarding magnetars, what's their relation with pulsars?
Right. Magnetars do seem to be a form of pulsar. They are ones with really even larger magnetic fields and more erratic behavior. They are less consistent. But yes, they do seem to be a form of pulsar, undoubtedly. And they are now suggested as being one of the possible sources for some, what we call fast radio bursts. The pulsar people are picking up single pulse, just one, very strong, very, very, very distant. What is it? That's the hot topic today. Fast radio bursts.
I think I remember there was one from 50,000 light years away that ionized the upper atmosphere of the Earth. and it was for 50,000 kilometers,
Yes.
light years away. So pretty impressive stuff.
Yeah, they're coming from things in other galaxies, way beyond our galaxy.
This is maybe a question that's also for our younger members of the audience, because how did your fascination with astronomy first and radio astronomy after was born? So what sparked your passion in this field?
At about age 11 or 12 in Britain, you move to a new school, secondary school, and you start doing many new subjects. So you start doing science and French, and we still do Latin and geography and history. As soon as we started doing science, I found I could do it and I liked it. There were very few girls in the class. Girls usually did needlework and cookery, and the boys did science. But 3 girls did science. I was one of them. We did physics that first term, and I came top of the class, beating all the boys. And I continued good at physics, okay at chemistry, biology, boring, no. Maths, okay. And so as I went through school, I was thinking, okay, I will do a physics degree at university. That gives me many, many, many different routes, futures. Which one will I take? And I read an astronomy book by an English author called Fred Hoyle. Fred Hoyle is talking about these big, Hoyle, yeah, is talking about these big galaxies that rotate. And at school in physics, we are doing motion in a circle. What happens, the forces on a body when it goes round in a circle? I thought, physics is good for astronomy. I'll be an astronomer. And I thought, no. You have to stay up at night to be an astronomer. I like my sleep. Radio astronomy. I will be a radio astronomer. So that's how it happened.
Because you can use the radio telescope also during the day.
Because stay up at day.
But I did some observations at night in the end.
Yeah.
For example, I was studying extrasolar planets with the transit method. So it's
Right.
night or either night. You cannot do any other way.
Yeah.
And it can get quite heavy when you stay up like 14 consecutive nights during observation during the winter, when you have 16 hours of astronomical nights to exploit. So it can get quite interesting.
Yes, you get very tired.
Yeah.
You close the cupola and the dome, the telescope dome, and everything else. You went home at 8 a.m. and at 3 p.m. you're again inside the dome, opening back the telescope because it's again night. We are not as north as the UK here in Italy, but still the winter nights are very long.
Mm-hmm. Mm-hmm.
A question from our follower.
Yeah.
As a scientist, what is your relationship with the humanities and social sciences?
I have an interest in poetry. I collect poetry with an astronomical theme. Mm-hmm. There's quite a lot of poetry about stars and galaxies and comets and meteors. And so I have this big collection of poetry, which I very much like. I also find that when I do talks about astronomy and poetry, my audience has many more women than if I do a talk about just astronomy. It's a good way of introducing more people to astronomy.
It's a hook. In some sense.
Hook. Yeah, but it's also lovely in itself.
I was wondering, in your collection, your astronomy poetry collection, do you have Leopardi?
Say again?
Leopardi.
No. I
He
don't
was
think.
an Italian poet. He's one of the founders of modern literature here in Italy. And he wrote a poem about the moon. It's just called Luna, the moon. And it's a beautiful poem, excruciatingly beautiful poem. I really advise you to go and look.
Is it in Italian?
It is in Italian, of course, but I guess you could find some translation around, because leopards, literally is like in English, leopards. Leopardi was it's a very big name here in Italy, so probably you may find some translations.
Speaking about poetry and astronomy, I have to remember the golden record. So aboard on the Voyager spacecraft, there is a map based on pulsars.
Yes.
So alien civilization can find our solar system using this pulsar map. There are 14 pulsars, if I remember correctly. So it's another very important thing related to pulsar. So just one question from Diego Ruotolo. If I've understood correctly, you realize that pulsars are neutron stars after Pacini's discovery. If I remember correctly, at that time you didn't know what this star was, of course. And the first input comes from Hoyle, if I remember correctly, during a talk given by your supervisor.
Yeah, that's right. Yes, that was remarkable.
Yeah.
At the time of the discovery, my supervisor, Tony, thought it was probably a white dwarf star, and it's oscillating and it's launching shocks. And somehow these shocks give radio waves. That was his favored model. The alternative one was something spinning. Now, with long observation, something spinning gradually gets slower and slower and slower, whereas something oscillating as it gets tired gets faster and stops. But we didn't have any information on the change of the period, and Tony was favoring this oscillation one. He gave a colloquium, a seminar in Cambridge just before the paper announcing the first one was published. We had kept it pretty quiet because we were scared that there was some ordinary explanation and we were going to look fools not thinking of it. So very little knowledge of this had leaked out. And everybody in Cambridge came to that colloquium announcing the discovery. Fred Hoyle sat in the front row. And Tony said what we'd found and gave his picture of an oscillating white dwarf. And at the end of the talk, Fred was the first one to speak. And he said in his best Yorkshire accent, "I don't think it's a white dwarf. I think it's a neutron star rotating." And that man, within 40 minutes has hit the right explanation, knowing nothing about it when he came into the room.
I was just wondering, the oscillating white dwarf model kind of remind of astroseismology, which was born decades later, because stars do oscillate, not to explain that part, but it's a fundamental part in exoplanetology, the astroseismology study of stars.
Yes. But quite hard to think of any mechanism that gives you pulses. When you didn't know they existed, you're starting, as we say, from code.
The point was that it was so small. Either the object was big and rapidly oscillating, or very small and very rapidly rotating, but the intensity suggested a large object, so everything was a mess. But in the end, you came up with the right explanation. Otherwise, we wouldn't be talking about this. I was thinking that maybe Pacini's is not describable as a discovery, but as an intuition. So he had a problem of the glowing of the nebula, and he proposed as explanation a neutron star with a magnetic field. And then you just found out that these things actually exist, but you didn't know about each other at the time, I guess.
No.
So this is beautiful because we have either pure experimental discovery and confirmation, and the other side, the theory, the physics, and that tell us how the world should be, and then the experiment that actually finds this thing, like gravitational waves or black hole collisions and all that kind of stuff, gravitational lenses. Einstein discovered, predicted them. People discovered them, and then they remembered, oh, but Einstein said this. So that's very beautiful.
Yeah, it's true.
Yes. Yeah. Physics is necessary for astronomy.
Yes.
We are crossing the hour mark. I don't know if you want to take another couple of questions or if you're fine.
I'm happy. Yes, if you're okay.
Okay. Yeah. There is an important question from Lucia about the imposter syndrome. So thank you very much for your lesson, Jocelyn. You're so inspiring, of course. What would you suggest to a young scientist to be who is suffering imposter syndrome right now?
Right. I would suggest she works as hard as she can, does her best work, and she will probably impress everybody, and people will recognize how clever she is, and she will be able to go on to whatever career she wants to do. So if you suffer from imposter syndrome, work hard. You will convince other people and maybe even convince yourself that you are clever.
Yes.
Dr. Bell, in 2018, you received the Breakthrough Prize, and you donated all the $3 million prize to fund women and other minorities, underrepresented minorities, in pursuing physics and academic research. My question is, why did you do that? Why it's important to do things like that, and how much work needs to be done in the field of gender and minorities field?
Yes, I think Italy is rather better than Britain, but probably even in Italy, in the physics department, you have more men than women. Yeah, yep. It's quite striking in Britain. I think Italy is rather better than Britain in this respect. My thinking was this. I ended up one of very few women in radio astronomy research, well, even in physics. And I felt in a minority, and there will be other people who feel in minorities also. If they are given the chance, they will probably work very hard. Maybe they will discover things, and they will improve the gender balance or the racial balance or whatever balance we're talking about in the department at the same time, and make it that little bit easier for the next women or the next colored person or the next disabled person and so on. So it was out of my own experience of being in a minority and suffering imposter syndrome and solving it by working hard. I thought, if I can give more people like the young Jocelyn the chance to do research, they will probably work very hard, and I'm sure they will find interesting things. And with luck, they will feel able to go on for a whole career in physics. So that's the logic, if you think it's logic.
The situation is very bad also here in Spain. I'm living in Spain, and the situation it's quite similar. So, unfortunately.
I kind of remember that in my faculty, it was Filippo, you're muted. Go on, Filippo.
Diversity is also good for science because a more complex group is also a more creative group, and a more robust group. So minorities are important also for the science sake.
There's been research by a management company in the English-speaking world showing that a company, a business that is more diverse is stronger and more successful. So I think the same might apply in university departments. Make them more diverse, they will be stronger, more robust, more creative. I hope.
Well, we have scientific evidence supporting this data.
Yes.
Diversity increases efficiency, science outputs, and production in general. I can remember that in my year, during my faculty year, there were 30% or less women. And as I progressed with my studies, the women became less and less. And that's sometimes I think it's called the leaky pipeline. So that it gets narrower and narrower for a woman to get to the top, or the glass ceiling that we were talking also about Hillary Clinton and his campaign. Do you think progress has been made in this sense, fixing the leaks?
It's getting better. There is improvement. The initiative that we started, that the funding bodies took on, please tell us how many women, how many men, what the women's salaries are, what the men's salaries are. That ended up with a very heavy bureaucratic load and was abandoned. But if they could keep it simple, I think it would be useful.
Okay, there are a number of similar questions, so I try to let's
collect
see
them into one.
Yes, exactly. So something related to the future of astronomy and also the future of pulsars. So in your opinion, what's the most exciting development about pulsars we could see in the next years? And another similar question is that what received online, so on our Instagram channel, what astrophysical discovery would you like to see in the next few years? And the third question, well, we can start with these two questions. Sorry.
Yes.
Thing that I'm really excited about now is a whole new way of looking at the universe. It's called gravitational radiation. I will tell you another little story. When I was an undergraduate in Glasgow, in my final year, my tutor was a curious little man called Ron Drever. He was very clever. He was fascinating and showed us a lot of interesting things in physics. No use helping us with the coursework, no, but showing us the future, yes. And I made a mental note, watch the fields that Ron Drever works in. And he moved into gravitational radiation fairly early on. And he was one of the pioneers of gravitational radiation. I decided I would watch the development of gravitational radiation telescopes, detectors. I was not sure I would still be alive when there was a detection, but there's been detections and I'm here and it's huge fun. It's a whole new spectrum that's opened up, a whole new way of doing astronomy. And that for me is one of the really exciting things at the moment. The results are coming in really quite fast. So in the north of Italy, there's Virgo, which has been playing an important part in these detections. Most of the detectors are in the USA. One come online in Japan. India is building one. That, for me, is one of the most exciting new topics in astrophysics, the detection of gravitational waves.
What about dark matter? I would love to know what that is.
Yeah, I think a lot of us would. And dark energy while we're about it, please.
Yeah, well, what about it? But I guess the question is, provided that we all want to know what those are, your most exciting field of interest is gravitational waves right now.
Yes. Yeah.
There is another question strictly related to pulsars. So this is the question. How do you think the recent discovery of the very long period pulsar will affect the research in the field? Thanks.
Yes, I don't know a lot about this one. The understanding of pulsars is that they spin very fast when they're young, and then they gradually slow up and sort of boom. So this is interesting. There's a possibility that pulsars might die and then be reborn a bit. Maybe die and reborn several times. Maybe that's what's going on. It's not clear at the moment. And of course, when you only have one, it's difficult. We need some more pulsars like that, please.
Just my question about it. I may already know the answer, but it's just for our viewers. What do you mean by dying? So what do you mean when a pulsar dies?
Okay, so a pulsar is spinning and it's sending out a radio wave. So it's gradually losing energy and getting slower and slower and slower. And finally, it's not going fast enough to give a radio wave. So the radio beam stops. Then we say it's a dead pulsar. And we're seeing pulsars moving that way towards dying. So we've got some idea of how pulsars die. Well, we think we have some idea. To find a pulsar that doesn't fit that is interesting. But if there's only one, maybe it's had a very special life. Maybe some other star has bumped into it or something peculiar happened. If we could find lots, well, at least several like that, we'd be in a much better place for understanding. So more, please.
Keep
Yes.
observing, keep discovering. It's always
Statistics.
about that. We need more data.
Statistics is quite important in astronomy. So
Yes.
Yeah, so when the pulsar dies, the neutron star stays. It's just
Yes.
quiet.
Yes. It dies because its magnetic field goes, or because its spin slows so much that it hasn't enough energy to give out a beam. It's still physically there and still spinning, but spinning slowly, and maybe not with a smaller magnetic field. So no pulses. Not enough energy, not enough zip to give pulses.
And how could you rebirth a pulsar, a dead pulsar? Like spin it up, I guess.
Yeah, you could spin it up, possibly. If it were to accrete material on one side, that might, well, it depends which side, but it could spin it up, for instance.
The vampire stars, as they call them.
Just
Journalists. They can be quite creative about that.
Oh, yeah. They give us some good language.
After all, astronomers don't know how to name things.
yeah.
Well, we're sometimes a bit technical in our language.
Yeah. We always say this to our followers, that when we present a new discovery, which is just a string of number and letters, we just say, okay, we cannot call it John, but we then proceed to explain it. It's a funny thing. Go on,
You know
Matteo.
how the name Pulsar came to be?
You told us.
I told you, sorry.
It's a
Yes,
fusion.
good.
It's a fusion of pulsating radio
And
source,
like
stellar radio
quasars.
source. It's
By
like
a
quasar.
journalist. Yes, like quasar.
Yes, by journalists, yes.
Also, blazars came very similarly.
A very important question, because we know that pulsars are used as cosmic clocks. I mean, so. But if a pulsar dies, I mean, slow down. Why pulsars are the best clocks we know?
Because they slow down very slowly over millions of years. So yes, they are slowing down, but it's very, very, very slow. And it's predictable as well. It's steady slow down.
Yeah.
So just by watching how slowly it's going down, you predict the period and you still have a good clock, basically.
This is also why we use pulsars as the cosmic map in Voyager, because we know that the pulsars slow down in thousands of years or more. So
billions.
Yeah, billions of years. So yes.
But if the little green men that pick up the Voyager satellite are clever, they will see that the pulsar period inscribed there is faster than the pulsar period today.
Yes.
So know when that plate was inscribed.
Yeah. Yes, exactly.
It's a dating system. That's amazing.
Dating system, yep.
Built in 3 dimensions, because we have also the galactic plane in the bottom side of the map.
We're talking about Carl Sagan.
Yeah,
yes.
He made that.
Yeah.
So we are deep beyond the hour mark right now.
Yes.
It's 1 hour and 20 minutes. So I guess it wouldn't be too kind towards Dr. Bell to keep her still in live with us and asking her questions. There are still loads of them, but most of them we actually have already replied. And I remind all of our viewers that we provide weekly live streamings in which we answer, it's Q&A live stream in which we answer to your questions. So you can save them for later and we'll just step in next time. Of course, it won't be Dr. Jocelyn Bell, but it will be. I hope it will be enough.
I just want to conclude with this comment, because it's a perfect example of the average level of our comment for you. So because the world audience is completely fascinated by your story, so it's an honor for us. So thank you very much. Thank you very much again.
And thank you for your help, and thank you everybody for the questions, which have been very good. But especially thank you 3 for all your help. Thank you.
Thank you to you.
And we are deeply grateful for this opportunity that you gave us.
Absolutely.
And thank you again. And hopefully see you soon, maybe live. We would really love to come and see some of your talks, puppet talks. I mean. Maybe in the future, who knows, when we can again travel safely.
Yeah.
So thank you very much still, everybody. Thanks to our viewers. Thanks to Dr. Jocelyn Bell for offering herself and offering her time to us. This live streaming is recorded on our YouTube channel and Facebook page. It will be subtitled in Italian in next days, if I have enough time to do that. But again, thank you everybody for watching, and see you soon. See you again.
Thank you again, Jocelyn. Thank you very much.
Thank you for the opportunity, and thank you for your help too.
You're welcome.
Good night, people of the stars. Good night, Dr. Bell.
Good night.
Bye-bye.